So, how do we know how old any of the rocks are on Earth? Well, one way we figured out how to um, date these rocks is just by relative dating. That is, figuring out what rock forms formed first, second, third, and so on. It tells us a sequence, but it doesn't tell us exactly how old different rocks are. So, we have a few different principles for relative dating. The first is the law of superposition, meaning that if we have a bottom layer, a middle layer, and a top layer of rock, the bottom layer is going to be the oldest. The top layer is going to be the youngest, which makes sense, right? You can't have an oldest layer on top. It has to lay on top of other rock. Then we have the principle of original horizontality. That just means that when rock gets laid down, it gets laid down flat. The principle of cross-cutting relationships is if there is a cut that happens into a layer of rock, and let's say it's magma that intrudes, it is assumed that that magma that is introduced into that rock is going to be younger than the rock itself. Then you can go ahead and take a look at some of these other principles, but those three tend to be the most important for relative dating. So here's an image of the Grand Canyon, and based on what we just talked about with relative dating, this top layer is going to be the youngest layer of rock of the Grand Canyon, and it's just going to get older and older as we go farther and farther down. Okay, here is an idea of we have original horizontality. All the rocks get laid down horizontally, but then there's deformation that happens, and this is pretty common. So some deformation can occur, and then erosion can occur. So now this very young layer is on the same level as this middle older layer. So there are different ways. If you cut across here, you'll see that, okay, this is young, this is getting older, this is old, and then this is pretty old. But if you are here, this rock may seem young if you didn't know about these layers over here. So relative dating is useful, but it does have some issues. Other geological evidence are fossils. So we have unaltered remains where, like teeth, bone, hard parts of an animal make good fossils. Altered remains, petrification, the cell wall breaks down, and then solid materials replace the soft tissue, creating minerals. And conditions that favor fossil rapid burial. If something is buried really quickly, it tends to fossilize a lot better than something that is out and open to the elements. If it has a lot of hard parts, like a shell, it's going to fossilize a lot easier. And then we're able to use fossils to interpret environments. So we might find coral fossils in places that don't have an ocean right now. That tells us that there used to be an ocean there. Now, a more accurate dating technique is radioactive or radiometric dating. This is where we look at isotopes and their half-lives in rock. We're able to see that half-lives of different isotopes in rock tend to be 713 million to 47 billion years old. So we're able to look at these isotopes and see how long they've been decaying for, and then be able to tell exactly how old rocks are. But notice that this is so long, 713 million to 47 billion years. So for anything that is younger, we're going to use carbon-14 dating. This is for more recent events. So carbon-14 is for anything that's living or has lived and is close to the surface, tend to be dated by carbon-14 a lot better than radiometric dating. Radiometric dating is good for rocks that are really deep, really, really old rocks. So radiometric dating, really old stuff. Carbon-14, relatively young stuff. Okay, so your two assignments for this week, we have Earth Structures and Processes worksheet. That's open note. Make sure to take a look at that. And then continental drift, differing viewpoints. You're going to look at differing viewpoints and then answer some questions based on the reading. Have a good week.